Yeah? Or to wait for the light? Ah, okay. Then, hi, I'm Tim, and today I will present you the results that the Duisburg team compiled in the roadmap project, and start with a short motivation. Yeah. As you know, like dust clouds and ice clouds are prevalent in the Martian atmosphere, and from time to time, even the whole planet is enshrouded in a sphere of dust, basically. And the project roadmap, as many of you know, stands for role and impact of dust and clouds in the Martian atmosphere. And while most of you did just that, the lab team didn't. So we focused on how the dust gets into the atmosphere in the first place and not the dust that is already in the atmosphere. And for that, there are several mechanisms on how the dust can get into the atmosphere. That would be direct lifting, where we have wind that acts a force on the particle that lies on the ground. And depending on the cross section of a particle, the force is bigger or smaller. And depending on forces like gravity and cohesive forces that hold the particle on the ground, the particle is either ripped off the ground by the shear stress of the wind or it's not. And there's a certain threshold that describes that. However, there's a problem on Mars for the smallest particles that can be lifted. That would be that the atmosphere is very thin. So particles that are suspended in the atmosphere for a long time are rather small compared to the Earth. That would be only a few microns. And for those small particles, the cohesive forces are very strong and the cross section is very small. So the wind would need rather to act as a rather big force to separate the particle from the ground and lift it off. And additionally, yeah, this through the not so dense atmosphere, the particle would also have to have even more speed, basically to act this force on the particle. Secondly, there would be dust devils that could lift the dust. However, those are hard to replicate in a lab. And even though that might be promising to lift dust from the ground, we did not focus on that either. So lastly, what we did focus on was saltation, which is some sort of direct lifting where we lift larger grains from the ground. For those, the cohesive forces are relatively smaller than for the fine particles, and thus they are lifted more easily by the wind. Also, they have a larger cross section that the wind can act on. However, they are far too large to stay in the atmosphere for a long time, and so they fall back down. And at each re-impact, the kinetic energy translates into breaking bonds of smaller particles that are then ejected and can be carried away by the wind. And that's what we focused on. So here's a sketch of one example of a separatation path where a particle is loosened by the wind, goes up a bit, accelerated by the wind, and then drops down. And at the re-impact, smaller dust is ejected, and that's exactly what we focus on. Then the saltating particle bounces up again and, well, does it the same thing a few more times, probably, maybe many more times. However, we just look at these impacts and at the dust that is ejected in these impacts. And yeah, in the course of the roadmap project, we analyzed several aspects of these particles that are ejected, which would firstly be size distribution. So we wanted to know if particles that can be suspended in the Martian atmosphere for a long time are ejected in these kind of impacts. Then if there's a particle distribution that can describe them, maybe a power law. And lastly, what masses of particles that are capable of long-term suspension are ejected. Then next we focused on the aerodynamic properties. We wanted to know if these particles are aggregates, if they are monolithic, and we analyzed axis ratios of particles as well. And lastly, we focused on electric properties. That did not finish by now, but we are still working on it, but we have some preliminary results to show. Where we analyzed particle charges in an electric field and also did some conductivity, a new setup for conductivity measurements. Okay. So firstly, I will introduce you to the experiment. This is basically the core setup, which remained the same throughout all the experiments. Everything around it, where we analyzed the ejector, changed for the different parts, but this remained the same. And what we have here is a particle accelerator, not the fancy kind like they have in CERN, but a bit more dusty, where we have some impactors of 180 to 250 micrometers, and those are accelerated by such a bolt, and they fly then onto a dust bed and impact with around 1 meter per second. And then these ejecta are subject to our science. Yeah. So as I said, firstly we searched for distribution of sizes for the ejector. We wanted to see what sizes are ejected, what is a particle size distribution, if there is any, or how does it look, and lastly, down to what sizes do we have particles that are ejected. So for that, same setup again. Basically, here the basis, and then around we placed microscope slides to each side of the dust bed, which we used to collect the smallest particles, because those, as I said earlier, have high cohesive forces and would stick to the microscope slide. Additionally, we placed copper wires to each side of the dust bed, where we put a high voltage of 5 kilovolts on to produce an inhomogenic field. And our idea was that some particles may carry a charge or dipole moment, and with the inhomogeneous field, we would drag them towards the microscope slides and enhance our capture efficiency. Yeah, on the right, basically the same, just how it looked in the chamber. Not so nice, but yeah, that's how it looked. And yeah, here's a photo of our data. It's not very spectacular, just some white dots. But I thought I would show it. And yeah, we basically took the area of each of those small points and translated that into a sphere or a circle with an equivalent diameter, and then took that diameter as the size of the particle. And then we binned all sizes and counted them, so that we could have a size distribution. And that then looked like this, where we had 2 data sets with an electric field and 2 data sets without an electric field. We had some restrictions on our data because we had to cut off all data below 0.5 micrometer due to the resolution limit of our optical microscope. However, we still took that as some qualitative results to see that we even have particles in that range. We could not just not really vouch for their accuracy. So, well, that we left a bit off. Then we cut off all data above 5 micrometer. Since we didn't see those as relevant, since the particle size that is generally believed to stay in the atmosphere for a long time is around 3 micrometers in diameter around, and additionally those larger particles don't stick that easily to the slide anymore. So we thought we cut them off at 5, so we have one nice order of magnitude here. And yeah, basically we have now two data sets with an electric field, the yellow circles and the red rectangles, and we can see that they are almost identical and that they follow a power law. The two data sets without an electric field, those are the black crosses and the blue rectangles. Um, those show some more variety, but overall also follow a power law. They have the same trend, which is indicated by the dashed line. Um, what just can be seen is that we have a drop in uh, efficiency, so we captured less particle, as also can be seen here on the y-axis. That's the absolute volume, so we captured absolute less particles than for the runs with an electric field. So we think that it definitely had an effect. So particles, there are definitely particles that carry charges or dipole moments. And yeah, we will come to back to that later in the part about electrical properties, because yeah, that was the indicator to see, yeah, maybe there is something. Um, yeah, so now we have our uh, particle size distribution, and we wanted to take that and see what masses of particles are ejected. And for that, we took that initial particle size distribution of the dust bed, which is the top here with the orange or here brown triangles, and basically took that as an initial thing, and we simplified that to be flat. I mean, that's quite a stretch here in this range, but we wanted to set a first benchmark, and for that it was sufficient. So we did some integration to cutoff diameter of 3 micrometers, and then yeah, basically saw that 0.02% of impactor mass are ejected for particles up to 3 micrometers. When we set it in relation to number of impactors and impactor mass. And so that was a nice result. I mean, it sounds not like a lot, but in those saltation cascade, we have several particles, or not several, basically a whole lot of particles, and those re-impact onto the ground a lot of times, so that adds up. And we think that's a reasonable process that can suspend dust into the atmosphere or bring dust into the atmosphere. Yeah, and then additionally, a short summary, we also found here that size distribution, and we saw that indeed particles at the smallest end of the size range are ejected as well, and those bonds are broken and can be ejected into the atmosphere. So next, we focused on the aerodynamic properties, where we analyzed sedimentation velocities of particles and compared them to theoretical values, and we wanted to see yeah, how they uh, compare, if we have aggregates, if we have some other anomalies, and for that also looked at particle shapes, although it's generally more comparison of axis ratio and not really in detail shape, so more like axis ratio if these are elongated or round. Okay, and for that we had the same experiment again, but different. And we removed those microscope slides that were here and indicated by those neatly drawn brown lines. The particles now sediment down the chamber and are analyzed with a high-speed camera before a light source. And then we captured those particles again on a microscope slide below and looked at them at an optical microscope, but now for shape and not for size. Because size measurements could now be done with a camera as well. Yeah. Here once again, real picture. Here on the bottom would be a microscope slide. And now we have a video. Well, by those lines indicate the sedimentation path, just to show you basically the data. Could you start it? Thank you. Oh, yeah, then it's not very spectacular again, but well, that's raw data most of the time. you can see those particles falling down. And from those videos, we got sedimentation velocities and particle sizes. Those lines are basically just a guide for the eye, because normally maybe you wouldn't see. And those go chronologically from blue to red. Now the last one is through. And we compiled those velocity and size data in the following plot, where you can see sedimentation velocity over geometrical size. That's the size that we took from the high-speed camera footage. And those are also our data points. Here on the top, the dashed blue line that indicates a particle that is free falling from the height of the dust bed, so basically the maximum velocity that could be reached. And what puzzled us a bit was here this area where we have around 30 micrometer, a huge span of sedimentation velocities, from even below 0.1 meter per second up to almost 0.5 meter per second. So having a factor of 5. And we thought that could have either been explained through particles that are very irregularly shaped and increasing the drag and thus falling slower, or we have some aggregates because that would decrease the effective particle density, and thus again particles would fall slower, or it's just a combination of both. And in the next step, we first compared it to theoretical values. So, I will explain the plot, but first I will explain the aerodynamic size, because on the y-axis we have aerodynamic size over geometric size. And basically what that is, we took particle velocity, put that into the model. I say model, but it's basically just a force equilibrium of gravity and drag force, and put the velocity in and let the model give out a size for a monolithic and spherical particle, and then compared the both. So here you see for round and monolithic particle that would just return the same thing, and it would be 1. And for an aggregate, just here shown by a hollow sphere or hollow circle, it would return a monolithic particle that is effectively smaller than the particle that we began with. So it would return a ratio of smaller than 1. And so we named those two regimes fast regime, because particles, so with ratios greater than 1, fast regimes because particles are too fast for their size, and slow regime because particles are basically too small for their size. And yeah, here for as a reference, this two lines here, the blue or the red line here, correspond to a 50% filling factor, meaning a particle that would be spherical, but having 50% porosity or here filling factor, or it would correspond to a monolithic particle with a 2-to-1 axis ratio that falls with a long axis towards the airstream. And we see that most particles are even below that line, so we either deal with highly porous aggregates or very elongated or wide particles, or just a combination of both. And firstly, we looked at axis ratios. So yeah, for that we did this again. But now we looked at longest axis to smallest axis that can fit through such a particle, and for the size we did the area equivalent circle again. And what we found was this scatter plot here. See a lot of points, it's 5,000 points about. And we see that most particles, about 90%, are in this 1-to-2 ratio regime. So most particles are generally rather round, and only about 10% in this 2-to-3 regime, and the ones above 3 are almost neglectable in count. And yeah, basically from that we concluded that this huge gap or many particles having such low ratios is probably not only because of axis ratios or shape. And so we looked at yeah, scanning electron microscope pictures of these particles because optical microscopy wouldn't let us see the morphology of these particles basically. So we took a deeper look and we could classify these particles basically in three categories. That would be small aggregates, which is here the top row, large aggregates, which is the middle row, and monolithic particles, which is here the bottom row. And I will show you an example of each one. Here's one small particle in an aggregate that can be seen, which basically entirely consists of smaller dust of 1 micrometer in size and smaller. Only a few particles in that aggregate are larger. Then we have here, which we think was an aggregate, now isn't anymore, but generally what led us to believe that was that we have a sample holder that was very sparsely covered in dust. And so having this area which such densely packed particles and aggregates, we think that this probably was a larger aggregate that was very porous and then just shattered upon impact. And that would also make a lot of sense in our rationale, having porous aggregates, which was in the plot I showed before. And lastly, we saw also these monolithic particles where we have yeah, basically one large grain, but yeah, some dust and smaller aggregates adhere to it, but that is quite common. And yeah, in shapes, we generally also saw these rather round shapes, so nothing surprising there. And coming back to that, now in conclusion, we thought that these particles down here most likely are aggregates. They obviously aren't perfect spherical because nothing in nature really is, but they aren't really elongated or cluster aggregates, something like that either. Rather, yeah, as I said, rather spherical. However, if we assumed them to be perfectly spherical, we would come up with a distribution like that with porosities, yeah, that are very high. So yeah, most likely because due to real effects of shape, and this would shift to the left. But yeah, you get the picture. Those are probably very porous things. Um, Lastly, we came to the electric properties of particles, where we measured the trajectories of particles in a field of 100 kilovolt per meter, was it? And yeah, basically their x deviation in a field and measured their acceleration and size, and from that charge on the particle. And now I have a picture of the setup again, probably. Ah, yes. So we here have the same thing again, dustbed, capacitor, and then now here's a plastic plate that wasn't there before. We just wanted to see them fall, but in the frame that we have, there's basically just 2 millimeters of height, and we didn't see an X deviation in that short time span. So we put a plastic plate here to see them rebound and analyze particle parabolas, so they stay longer in the camera frame. Um, and also we got data from that. However, then we thought maybe they interact with the plastic and they are charged differently than they were before. So we changed that again and put a dust bed here on the plastic slide and let the saltators basically drop down and then let them impact in the field already so that the particles are ejected in a field. And we would analyze the ejector that come out of dust-dust interaction and not with an interaction with plastic. So for that, I probably have another video. And now this will be quite the spotting game because here we have an impactor and this will eject two particles. One flies at the bottom here, and another one will come into view around here, and it goes to the right and will bend back. Maybe you will see. So, attention. There. Okay, maybe once again. Here. Yeah. And that was quite fascinating to see the particle just bend backwards. So yeah, from the acceleration in x direction and sizes, we then calculated to the charges and ah, put that all together. And yeah, thank you. In this plot, where we see particle charges and generally particles, we have many particles with a charge around 0, which yeah, is not so surprising. But we also have many particles that are charged. And I mean, you have no comparison, but I will show you soon. So that's not so little of charge. We have here 10 to the power of 13 electrons per square meter. And the only thing that we don't know of that, I mean, particles are definitely charged. We did see that. However, we are not certain where this charge comes from. It could be that we have some triboelectric effect, that particles, when they yeah, have dust-dust interaction, they have friction and then triboelectrically charge the ejector. But it could also be because we have a strong electric field and the dust might be slightly conductive, that we have a charge separation in the surface, and then when particles impact a certain spot, they are pre-charged positively, which would, for example, this some sort of bias that we might see here. We are not sure yet because we did some more experiments and will yeah, back that data up to see if down here maybe is something as well. But this would maybe speak for some sort of bias. Yeah, but we will come back to that in some more experiments that we do. But now, as for comparison, this is work done by another member of our work group, and she did collision experiments with aggregates in a high electric field as well. And yeah, basically, even though this is a different unit here, I translated that to the same as the graph here, and we see almost yeah, the same numbers. So this is definitely on the same order of magnitude and very similar results. So we might deal here with the same effect. And to investigate if this is triboelectricity or conductivity, we now made a new experiment. This is very simple again, but basically just measuring the conductivity or resistance of some of the material, and from that we can then estimate how the conductivity of the material we used, and depending on the grain size and such is. But we don't really have results from that yet, so this is just a concept. Yeah. And so in conclusion, we analyzed these saltating impacts, so the ejector, and saw that even fine dust that can be suspended in the Martian atmosphere for a long time is ejected. That can be described by a size distribution, and that relevant amounts are ejected in each impact. Then we saw that we probably deal with particles that are highly porous in these ejector as well. And lastly, that we have particles that carry charges. However, we are not yet certain where this charge comes from. And now I will skip over the acknowledgements page, and thank you for your attention.
So in the first part, you seem to show that when you have an electric field, it doesn't really matter. But in the last part, you show there are electricity. No, the way before that.
Yeah,
the plot.
yeah.
Yes, in this one, when I saw that one, I said, okay, so apparently electric field, we don't care.
Hmm?
And now in the end, you show that they are charged, quite well charged. So I'm confused. How do you make sense of these?
Well, I mean, we definitely have here a higher output of particles with the two runs with an electric field than the two without an electric field. That's both around 5K particles that we found, and that's 1 in 3,000. So we definitely gained a lot more with an electric field.
That's particles that were set aloft somehow, right?
Yes. But
I just don't get how the electric field helps.
I mean, that's in the last part we measured that Pesky is the same. We have an impact, and we measured that there's charge on the particles, and here we see an impact, and if we turn on an electric field, we have higher output of particles, so we capture more particles. So those particles that would be lost otherwise, we capture them with an electric field. Well, that speaks for them being charged as well. Yeah, exactly. Hmm.
Okay, just wondering because the velocity measurements you make are from images.
Yeah.
So do you have any idea of the uncertainty due to the depth part, which you don't resolve in your image?
I mean, we have the field perpendicular to the image, so the depth shouldn't really matter because they're in the middle of the field and the field should stay the same a bit in front and back. And we only analyzed x direction. So if it moves in z or not, wouldn't really matter. That would only be the initial velocity, and that might not, that shouldn't change basically.
So I have a question and a comment. The comment is that in our studies, we saw contact electrification giving charges up to around 100 electrons per square micron. And your value was
per square meter.
13.
10 to the power of 13, but per square meter.
Yes.
Yeah.
So yeah. So your value in my units is 13. Not an unusual amount.
Okay.
Through contact electrification.
I see.
It can be up to 100-ish, a bit more than 100. That argues that if it was contact electrification, then the amount isn't weird. It's
okay.
Good value. Yeah.
Yeah.
The question was, in my head, I'm seeing that you have a sand grain coming in, you're taking up at least one ejector. You talked about percentages and masses, but
yeah, well,
I'd rather know how many dust grains come up when you.
That's an average over around 200 impacts, so it might not be in every impact, but in others there might be more. So that might vary from impact to impact.
Less than one, or is it a lot more than one?
I think one is quite a little amount if you put it in volume. So I think that there would be at least one in each impact. Yeah.
I think it's more than one, yeah, that come up each time.
As for feeling, I would say yes, yeah.
Well, feelings are good enough.
Okay.